Okay, this is going to be a vodcast on the root mean square velocity of gases. What this really means is basically in a sample of gas, what is the average velocity of the gases in the particle, in the container? So some gas molecules will be fast, some of them will be slow, some will be in the middle. What is the average, basically speed? When we say velocity, we kind of talk about speed. There is an equation that relates this. And basically it means URMS means root mean square velocity, root mean square. In statistics, this is how they calculate a root mean square. So if you're wondering what that means, if you take in statistics, it is something that they use to calculate a different type of average, I guess you can say. It equals U squared radical, which really equals 3 times R, and R is the R constant, 8.3145 joules divided by moles times K. Temperature is in Kelvin, and M is the mass of 1 mole of gas particles in kilograms. Now, I don't know how many times people forget to convert the molar mass into kilograms, but it has to be in kilograms, not grams. The symbol U square means that the average of the squares of the particle velocities, and the square root is called the root mean square velocity, symbolized URMS. Again, there's a lot of statistics behind this. If you're familiar with statistics, you'll know what the hell this all means. But for the sake of chemistry, and for this class, you just have to know that URMS equals this equation. And the equations have these variables. Okay, so what this means is here a plot of the relative number of N2 molecules that have a given velocity at 3 temperatures. So if the temperature is very, very low at 273 Kelvin, this is what the distribution would look like of the N2 molecules relative to each other. So you're going to have a few that are at 1,000, and you're going to have a few that are at 0, but most of them are going to be in this range right here. Area underneath the graph would be the average velocity of that. You start to increase the temperature, the graph begins to spread out. The area in the graph for all three is all the same. It's just that the graph is now kind of spreading out to compensate for those different distributions of speed incomes, relative speeds of each other. So if you're at this temperature, you're going to have a lot more gas molecules now that are traveling at 2,000 or above this area than you would have had 273. So very different types of distribution of speed of N2 gas molecules in a container. And the area in all three graphs technically are all the same. It's just this distribution is changing as the temperature increases. Okay, so in a nutshell, the average increases as the temperature increases. It makes sense. As you increase the temperature, more and more gas molecules will start traveling faster, and then your average will start to increase. And basically your speed increases as temperature increases. It's kind of like a no-brainer kind of concept. So let's do an example. High above the stratosphere, the temperature of the atmosphere may reach 1,000 degrees Celsius. However, spacecraft and astronauts do not burn up because the concentration of molecules is very low, and the impacts transfer very little energy. What is the root mean square velocity of nitrogen molecules at that temperature? So we basically want to know what is the average speed of nitrogen molecules at that height. And again, we're going to use that R. So we're going to plug it into the formula. The only thing you have to know is, being AP Chem students, you should know how to plug values into an equation and solve it. So I'll let you go ahead and try it. Remember, your temperature has to be in Kelvin, so that's got to be converted into Kelvin. And we are talking about N2 gas. Where does it go? What is root mean square velocity? Nitrogen molecules. So nitrogen is N2, not N. And you have to find the mass of 1 mole of N2 in kilograms. So knowing that information, plug it in, solve it, and see what you get. Okay, you should have gotten this. URMS equals 3RT divided by M. 3 times the R constant times the temperature in Kelvin, which is 1273 Kelvin, divided by the molar mass of nitrogen, but in kilograms. So 0.02802 kilograms. And I got 1065, and the units is going to be meters per second. Meters per second is this average speed of the gas molecules in the atmosphere. So the units for URMS is going to be meters per second. So I'd like you to try one on your own. Go ahead and click pause and calculate the URMS of carbon dioxide at 25 degrees Celsius and see what you get. Okay, so using the formula, 3 times R times the temperature in Kelvin, so 298 Kelvin, divided by the molar mass of carbon dioxide, but in kilograms, and we got 411 meters per second. Okay, so there you go.